Hi there and welcome to PhD at Living. Today we're going to talk about one single element. Just one. Diamonds, carbon nanotubes, pencils, and Buckminster fullerenes are made of this stuff. So without further ado, let's talk about praseodymium. I'm kidding, it's carbon. Carbon's smack at the top of group 14 on the periodic table, so it likes to make 4 covalent bonds. Carbon doesn't like to make ionic bonds because to do so would require it to either gain or lose 4 whole electrons, which requires a gigantic amount of energy, so not going to happen. Because of that high number of bonds, carbon can make a number of different bonds in a number of different ways. For this video, we're going to talk very specifically about carbon bonding to itself and only to itself. There are a number of different configurations there, but we're going to hit the most expensive one first. You got it, a girl's best friend, diamonds. You might think these different configurations are types of polymorphism, but that property is more for compounds. Because we're dealing with a single element here, only carbon, these are actually called allotropes. In diamonds, each carbon is covalently bonded to 4 other carbon atoms. This means each carbon in diamonds is sp3 hybridized and has the electron and molecular geometry of tetrahedral. It'll be easier to see through a drawing. Ow, damn it. It's a stupid drawing, that's all it is. You know how to do this, it's real easy, it's no big deal. Okay. As you can see from this really easy to draw structure, those sp3 hybridized carbons tend to make 6-membered rings, kind of like cyclohexanes minus the hydrogens. And if you look in the drawing, you can kind of see that each of those 6-membered rings develops into a chair, which is the thermodynamically most favorable conformation. Those chairs lead to 0 bond strain energy, meaning the carbons in diamond are about as happy and relaxed as an element can be. That also helps explain why diamond is so chemically inert and doesn't want to react with anything. Because the carbon-carbon bonds in diamond are oriented in tetrahedra, diamond has the highest number of atoms per unit volume of any of the allotropes of carbon. This explains why diamond is almost completely incompressible and so effing hard. These atoms are just so close together that you can't squeeze anything between them. This brings up a key distinction between hardness and toughness, which is the resistance to breaking upon impact. While diamond is incredibly hard, it's not very tough. That combination makes diamond a nice gemstone because it holds up really well over time, but can be cut into a number of pretty shapes and marked up 1,000-fold and sold to people. The color of the Hope diamond is, according to the Gemological Institute of America, fancy deep grayish blue. The reason is because of trace boron contamination in that carbon-carbon crystal lattice in the diamond. That to me says probably the most famous diamond in the world is just an impure piece of junk. But the idiocy of the diamond trade is for another day, so moving on. While there is some disagreement to this, graphite's used as the standard state of carbon for defining its heat of formation. It's also used for... Hang on there, Chief. Isn't diamond the standard state of carbon? Nope. Oh, really? Isn't it like the hardest organic thing on Earth and completely chemically inert? Pretty much, yeah. But it's not the most stable state. Nope. So you're telling me diamond is a metastable state of carbon? Yep. Well then how's it so stable? Well, technically it's just a really, really stable metastable. I know that's a junk answer, but it's the truth. The timescale over which diamond would revert to graphite at ambient temperature and pressure is like billions of years, so it's essentially forever. For what it's worth, above 400 degrees C or so, diamond will start to revert to graphite a little more quickly. And above 850 degrees C, diamond does start to oxidize a little bit. Graphite at high temperatures just stays graphite. So there. While each carbon in diamond has 4 sigma single bonds, each carbon in graphite has 3 sigma single bonds. It still arranges in a cycle. Whoa. Graphite carbons only have 3 bonds. Will you stop interrupting me? Yes! But carbon has to have 4 bonds. You're telling me there's just an electron floating around out there? If you'd shut up for a minute, I would tell you. Okay. Graphite's composed of a number of individual layers of carbon stacked on top of each other. Each one of the individual layers is called graphene. Each one of the carbons in a graphene layer has 3 sigma single bonds to other carbons. Here's a great example of graphene. You can see in this small network of carbon atoms that we have the same recurring 6-membered ring structure like we saw in diamond, but there are 2 big differences. The first is that each of these rings in the graphene sheets and in the graphites, when you stack them on top of each other, are planar. That means we have no ring softening and no chair conformations like we saw in diamond. The second big factor is that each carbon in graphene and graphite is only single bonded to 3 other carbon atoms, not 4 other carbon atoms like we saw in diamond. Well, if you only have 3 bonds, that means we have an electron hanging out that's not bonded anywhere. So what works with that? As it turns out, and this is so cool, it makes graphene and graphite aromatic. Let's look at that in 2 parts. First, let's take the hybridization of each of the carbon atoms. With this particular carbon atom here, we know he's single sigma bonded to 3 other carbon atoms. That means we have 3 sp2 hybridized orbitals to make those happen, but we also have one unhybridized mini p orbital that's sticking straight out at us, coming into the camera. Well, we know we have 1 electron that's just kind of hanging out there in that mini p orbital with each of these carbon atoms. Looking at our aromaticity rule, we know we need 2n plus 2 electrons in order to be aromatic in our ring structure. If n equals 2 here, we know we need 6 electrons. As it just so happens, we have 6 carbons, each with a single electron in that delocalized mini p orbital. 6 different electrons, 6 carbons, ring structure. Yep, we're aromatic. It's probably better to show some kind of resonance happening here in these rings, even though there technically aren't any double bonds like we would see in something like benzene, but it helps to show the electron delocalization. Interestingly enough, that aromaticity causes graphite and graphene to be electrically conductive. For what it's worth, graphene is the single strongest material known by tensile stress and Young's modulus. Also, the planarity of the graphene sheets makes them very easy to flake off the greater mother graphite structure, which makes graphite and graphene really good materials for pencil lead. Perhaps most interestingly, perfectly constructed graphene is chemically inert, so in order to get graphene and graphite to react with something, you need a certain minimal amount of irregularity or defect in the material. Graphite's also used as a dry lubricant. Because there are little pockets of air and water between the layers of graphene, and the graphene layers themselves slip past each other so easily, graphite displays a very high degree of lubricity. The only reason I filmed this whole segment was just to say the word lubricity. Lubricity. God, I love it. A long time ago, graphite used to be called plumbago. Again, I don't have anything else to say except I love the word plumbago. Okay. With this full understanding, we can see the biggest difference between the diamond carbons and the graphite-graphene carbons is just the hybridization of those atoms and the electron orbitals. This is what creates the wide difference in properties between graphite and diamonds, even though both materials are made up exclusively of carbon atoms. Next, we get to fullerenes, which are basically graphene sheets that are molded into 3D structures, such as tubes or balls. With as much trouble as I had drawing diamond, and for my sanity, I've decided to just ask you to use your imagination and pretend you see a really cool tube-looking thing here, and a sweet ball, and like an awesome buckyball. The buckyball is also known as the Buckminster fullerene, and it's a fullerene with 60 carbon atoms. It has an alternating 5-membered ring, 6-membered ring structure that kind of looks like a soccer ball. The Buckminster fullerene is the largest object, around 1 nanometer diameter or so, to be observed to have wave-particle duality. Carbon nanotubes are also included in this group. There's tons of current research about the carbon nanotubes, but it's not my forte whatsoever as a chemist, so I'm not really going to hit on them that much. That being said, the nanotubes are extremely strong and stiff, meaning they can have a higher L/D, length over diameter ratio, than really anything else ever. If you made a strand of fishing wire purely from carbon nanotubes, it would be strong enough to hold up a mature bull elephant. How about that? Finally, we get to the amorphous allotropes of carbon. Being amorphous doesn't mean there's no crystallinity whatsoever, it just means there's no global repeated crystallinity. These allotropes are things like charcoal, carbon black, and soot. I don't have a lot to say about these, except I will mention carbon black has an unusually high surface area to volume ratio, and that leads to it being used very well as a cheap, effective filler material. For instance, car tires are black because of carbon black. It's used to add a lot of strength to the rubber material in the tire. And those, my friends, are the allotropes of carbon. A simple unit cell difference that takes a pencil to an overpriced cartel product. See you next time. The diamond is not taking off of this godforsaken continent.